Hi, it's time for another math easy solution. Today we're going to discuss further into linear differential equations and now look at example 3. And that one goes over this example, which states solve y prime plus 2 times xy equals to 1. So first thing to do, like always in these kind of equations, is again recall from my earlier video that we want this in standard form, which is y prime plus p of x, or a function of x, times it by y, and then equals to q of x, or a function of x on the right side. And as you can see, this one is in fact already in standard form. Put it like that. Let's zoom in a bit. Yeah, so then this means that this p of x is equal to 2x, and then this right side, this one is just equal to 1, so that's the right side function. And then again, recall that the next step is to find our integrating factor, so thus I of x, recall the formula for it, is equal to e to the power of the integral of p of x dx. And in this case, it's going to be p of x is 2x, so this equals 2 e to the integral 2x dx. Yes, so now the integral of this is going to be equal to e to the integral of 2x. The 2 is just constant. Integral of x is x squared, so we'll have a 2 there, x squared, and then divide by 2. Those cancel. Then we also have to add a constant of integration, except as explained in my earlier video, we just simply choose c is equal to 0. We just need one particular solution. So then the 2's cancel, this is x squared, and this is I of x. And again, alright, choose c equals to 0 because we only want one solution. And you could learn more about this in my earlier video on the integrating factor. I'll put that in the video link below. And then recall the next step is to, well, multiply both sides of the differential equation. So we have y prime plus, let's go, plus 2xy equals to 1, and then we basically multiply both sides by this integrating factor I of x, which is e to the power of x squared, and then the left side is going to be e to the x squared, like that. And then when you expand this, like I've shown before, what you'll end up getting is basically this is all equal to d over dx, and then e to the x squared times y. In other words, the derivative of I times y is equal to this whole thing. And again, this is, you could see the proof for all this, and that's what this integrating factor is. And then you can see the proof for it in a linear differential equations video I did, the first one where I derived it all. So yeah, instead of proving that it's the same, yeah, just assume it's the same, which it actually is. Yeah, so then this whole thing equals to that, and then this brings it down. So then we have, this is 1 times that is still e to the x squared. So now that we have this, we can move this dx onto this side and then integrate it. So we'll have d of e to the x squared, and then times by y equals to e x squared dx, and then integrate both sides. So now the whole idea was to get a separable equation. Now we integrate both sides. This one is just itself, so e to the x e to the x squared y, and then you also have to add a constant of integration. It's for completeness. On the left side is plus c1. This equals 2. This one you can't actually solve this integral, and I'll explain why in a bit. This one, there's no actual solution in terms of elementary functions. Yeah, so the next step, I'll just move this onto this side, and then I'll change it into just a constant c. So then we have e to the x squared y, and I'll just keep this integral as is, equals to integral of e to the x squared dx plus c, and then where obviously this c equals to negative c1. Negative of a constant is still a constant, so just to make it simpler, just call it c. So now the next step is, well, we can divide both sides by e to the x squared to cancel this. So then let's divide this whole thing out by e to the x squared. So then when we do that, get rid of there. So then we finally have y of x is equal to, And then this part here, you could also flip it above and call it e to the negative x squared, same thing as 1 divided by. And then what I'll do is write this in the integral, e to the x squared dx. So this is on my calculus book, it has the final answer. And then plus c times e to the negative x squared. So there is our final solution. Yeah, and basically recall from my earlier video, can we integrate all continuous functions, that the integral of e to the x squared cannot be expressed in terms of elementary functions. And these are just the regular functions that we have all known, like trigonometric functions, linear, etc., and other types of functions. And I'll put that video link in the description below, you could check that out. But basically, since we can't solve it, but you can actually solve the integral. So here, if you go to this integral calculator, I will put the link here. Let's just open it up. So let's go over here. Okay, so this is pretty cool. Calculator, let's just solve it. Go. Okay, and then the answer that this calculator gets is... yeah, so then let's just see this. It's still loading. Yeah, so then the integration of this is square root pi times this ERFI of x, all divided by 2 plus c. And I'll get to what this function is in a bit. So basically what this means is that the integral e to the x squared dx is equal to square root pi over 2 and then ERFI of x. So this is a strange function. So yeah, so basically some more info on this function, where this function is known as the imaginary error function, which is yeah, pretty interesting. So it is a special non-elementary function that occurs in probability, statistics, and partial differential equations describing diffusion. And I got this quote from Wikipedia there, you can just go check it out. And basically, despite the imaginary label, this error function, imaginary error function, is real when x is real. I'll cover this in future videos, so stay tuned for that. I'm not going to go over too much on it here. And in fact, this is the first time I actually have heard of this function. Yeah, so I'll cover that in later videos. So what we have now is, so thus our function or solution is, if we wanted to solve this, and again, this using this non-elementary function. So then, just because I want to graph this eventually in this video, so thus y of x is equal to e to the negative x squared, and then we have this integral, and then that integral is this over there. So I'll put this in brackets, square root pi over 2 ERFI of x plus, and I'll put the constant as c1 because this we're going to combine it eventually. And also, yeah, so I'll take out this e to the negative x squared, just take it out, so we have the constant there. So we have a constant there plus this, and then we'll have c2. I'll just write this one as c2 just for completeness sake. And then I'll combine these together. So basically, when we're dealing with these constants of integration, yeah, so we always have to eventually add them up together. I just don't want to write c and ignore that we always have to add the constant of integration. But I just wanted to show that whatever the constant is when you do an integral, when there's already another constant, they just add up together, and you can combine them all together. Yeah, so then these constants are put together, so then this equals to e to the negative x squared, and then we have square root pi over 2 ERFI of x plus c. So I'll just keep it like that. So put this here, y of x, like that. And yeah, so the reason I put this error function inside is just so that we can graph it, because I couldn't find a graphing calculator online that can graph functions like this, where you have different functions plus integrals all in together. But the thing is, so then once you put it into this form, then you can actually graph it this Wolfram alpha. So I put the link here, so you can click it, and I put it with different values of the constant c. And as you can see, it's a pretty giant calculation. You'll see it doing. It's a pretty cool website. So let's just let it load. Okay, so it's still loading. Let's just see this. Okay. Equals. Okay, there it is. Yeah, so it's a giant calculation, but it's pretty cool how this whole site does it. So you put that in there, and they change how it looks to make it a bit neater. So there's our function, and is divided over e to the power of x squared. And this is for constants -2, -1, 0, +1, +2. I did that just so we can graph it out, and there's the graph how it looks like. From the x is from -1.4 to 1.4 to see how it looks. They all look similar like that. And then as you can see, eventually it's all approaching the same values at the higher values of x, the absolute values of x. On the right side and left side, it's all approaching together. So I've copied and pasted that here. Here's the functions, how they look like. So this top one, this corresponds to +2. So this is c equals to 2. This is c equals to 1. C equals to 0. And then this one is c equals to -1, and then this one c equals to -2 is over this one. So this is some pretty interesting stuff, and they all combine to get to this point here, and I assume it's approaching 0 on both sides. I haven't proven that yet. Yeah, now going further, just I want to make a note. In my calculus book it states another way of writing the solution is as follows: y of x. This is writing the solution including the integral, so this is e to the -x squared, and then we have from 0 to x of e t over squared. So the variables just change so that we can have this definite integral there from 0 to x dt plus c e to the -x squared. And yeah, so this one's exactly the same thing as this one here, except when you write in definite form. And so this is pretty interesting stuff. I just wanted to put that in my calculus book. My calculus book brought this up at the end. And also it states any number can be chosen for the lower limit of integration here, and that's because that value will just be accounted for in the constant of integration c. For example, if we chose it just to be a general one, so let's say y of x is equal to e to the -x squared, and I'll just take this e to the -x squared out of there just to make it easier. So now we have integral from 0, or not from 0, let's go from ax et squared, and then we have dt plus c. So when you take it out, then you'll have this constant out like that. And then when you integrate this, we end up getting e to the -x squared. And then we have, this is going to be equal to, this will be equal to, and I'll put this as, so then, the integral of this one we know is going to be square root pi over 2 erfi of t. And then we're evaluating this from, and I'll put this giant bracket like that instead, and then this one, so that we're integrating this now from a to x, and then we just add the constant c here, and then put a giant bracket like that, put a nicer bracket. Okay, so we have that. When we evaluate this this function here, or evaluate this answer to the integral, e to the -x squared, put a giant bracket like this. This one's going to be now square root pi over 2 erfi of x, and then we have to subtract with the lower part there. This is going to be now square root pi over 2 erfi of a, and then plus c at the end here. And yeah, so then regardless of what you chose for a, this is still a constant. So then this whole thing, we can combine it. We'll write this as d. Yeah, so then basically we can combine this all and then write this as e to the -x squared, and then we have square root pi over 2 erfi of x, and then plus d. And this is what we have, y of x. So this is just proving that it doesn't matter what value you pick for the lower end. And again, where d is equal to, I'll put c minus just to move it on the other side, c minus square root pi over 2 erfi of a, like that. And this is still a constant, a subtraction of two constants. This is just a function with a value in there. Regardless what that function is, if you have one value, it's going to be one constant value. So this is going to be equal to constant here. And then if you scroll up, this exact formula, this is the exact same thing we just graphed. So then we have over here e to the negative x squared times square root pi over 2 times the error function, imaginary error function, plus c. Yeah, in this case the constant c, the other one's constant d. They're the exact same thing, just a constant. So yeah, you could write it like this. I'm not 100% sure why my calculus book put it like this, but I assume it's something to do with the error function, how it's written. Anyways, I'll get to the error function in later videos, so stay tuned for that. Anyways, hopefully you enjoyed and followed through this pretty interesting example video on linear differential equations and a little preview of this imaginary error function. Anyways, that's all for today. If you learned, like always, you can download these exact notes in a link below, and yeah, stay tuned for another Math Easy solution.